Hey everyone, welcome back to 11.6. We're going to talk about area of irregular polygons. This section has a lot of writing, so it may be a good idea to pause and write down the information and then listen, or listen and then write down. And you may need to pause and maybe review the video again. So let's get started with our video, and you will see what I'm kind of talking about. So our first vocab word is the center of a polygon, and it's going to be the center of the circumscribed circle, and I think about it as just the center of the circle. So if we didn't have that figure inscribed in the circle, we would still have the center like we've been talking about before. And I have actually labeled that with that green dot right there, so I've tried to color coordinate these vocabulary words in my picture. The radius of the polygon would be the radius of the circle. You can think of it as from the center to the outside of the circle, or you can think about it as from the center to the vertice of the inscribed angle, and that's going to be something that will differentiate the radius and the apothem when we get to that. So the radius is just from the center to the vertice of the polygon. Our new word is called apothem. It's a little bit different, but it is the distance from the center to any side of the polygon. So I kind of think of it as it has a similar characteristics of the altitude that we know of. One, it's a perpendicular bisector, which means it splits the side into two equal parts and makes a 90-degree angle. So as you can see in our polygon, the right angle up top, that is going to be called our apothem. It also bisects the central angle. So if we find the central angle, we will know that the apothem splits it into two. And then last, to find the central angle, or what is it first, it will be the angle formed by two radii drawn to consecutive vertices of the polygon. So if I have two radii that I have drawn, that you can notice in that dark purple, it almost creates a triangle that we'll talk about a little later. And the angle that it creates by those two radii are called the central angle. And to find the degree of that central angle, you can look down here at my equation. You'll do 360 divided by the number of sides. Since we have 7 sides in this figure, I would do 360 divided by 7, which would give me a central angle of 51.43. So there's a lot of information right there, so if you need to pause it or rewind it or anything like that, please feel free to do so. I have also cut out, we'll do this a little bit more later, I've kind of taken out that triangle out of my inscribed polygon, and I've labeled the radii and the sides and the central angle, because those will be very important later in this section. So again, if you need to pause it, you can. If not, we'll keep on going. So the first example in our diagram, A, B, C, D, E, F, is a regular hexagon inscribed in circle G. And we want to find the measure of these angles given. Well, first let's find that central angle. We know that a hexagon has 6 sides, so let's say 360 divided by 6 would give us a 60-degree central angle. So we know that that angle is 60 degrees. So now that they are asking for EGF, so EGF, that would be our central angle, so we're just going to write that again, 360 divided by 6, or that angle would be 60 degrees. Next, we're going to find EGH, so EGH, and notice that that angle is created by the apothem and our radius. So GH is your apothem, which makes an altitude of an isosceles triangle EGF. So GH bisects our central angle like we talked about before, and the measure of EGH is 1/2 of our central angle. So we would say that that angle would be 30 degrees. And last, we want to find HEG. So HGE will be our last one that we're going to look at. So the sum of the measures of a right triangle equal 180 degrees. So if you look at that, let's redraw it out to the side. We know this is E, G, and H. We just said that EGH was 30 degrees. So we know the angle sum theorem would say that we're going to add all three angles together to get 180. So we could conclude that that angle would be 60 degrees. So continuing on with that. Again, there is a lot of information, so let's make sure that you pause it whenever you need to make sure you get all of it down. So before we start in with our theorem, we're going to look at how did we get to that point. So think about, I have a square, and I can draw my diagonals of the square, which create 4 triangles. So 1, 2, 3, 4. And I have redrawn them out to the side. So I know how to find the area of each triangle, and then I could multiply it by 4 to get my total area of my square. And before now, we had talked about our area of a triangle equaling 1/2 base times height. So that would be there, and I've drawn my height there. But notice that your height now becomes our apothem, and our base actually becomes the side of our polygon that would be inscribed in our circle. So where we really get our quote-unquote new equation for a regular polygon would just be the same as how we might think of it. So I have 4 triangles that make up my square, so that's where I get 4, and then I'm just going to take my area of my triangle, 1/2 base times height. Or we can think of it as area equals 4 times 1/2 our sides times our apothem. So that's kind of where they have come up with this area of our regular polygon. So let's look at our theorem 11:11. So the area of a regular n-gon with side lengths S is half the product of the apothem A and the perimeter P. So here is our equations that we need to make sure we memorize and know how to use. So you can do it both ways. So area equals 1/2 the apothem times our perimeter, or you can think of it as area equals 1/2 times our apothem times the number of sides times our side length. So I've rewritten it up here on the top, so I would highly suggest us writing that down just in words, and just so you don't forget what those letters mean. I've also designated N equals the number of sides, and S equals our side length that we've been talking about. So using that formula, you know that you need 3 things, the big 3, to find your area: the apothem, your number of sides, and your side length. So that's kind of what our goal is to find when we go through the problems. I have also kind of made up steps for myself that I thought would help. So let's go through those. We'll go through those after we get through our example. So we have our coaster. A wooden coaster is a regular octagon with 3 centimeter sides and the radius of about 3.92 centimeters. What's the area of the coaster? Alright, step 1 for them says the perimeter P of the coaster. We want to find that first. So looking at that, it's an octagon, so it has 8 sides, and we know that each side is 3 centimeters, so we can say 8 times 3. So our perimeter gives us 24 centimeters. Pretty easy, pretty straightforward. Now we want to find the apothem. Well, it's a little bit, difficult to see it right then, but we know that if we draw that perpendicular segment, we can almost create, not almost, I guess we can create a right angle, and we love working with right angles because they are easy to deal with. Alright, so we know that our RQ is 3.92 centimeters, and we want to somehow find our apothem. So the apothem is the height of our S, they called that point S, of that triangle. Because the triangle is isosceles, the altitude RS, again, bisects QP. So we know that this is congruent to that. And since they are 3, PQ is 3, we know that half of it is 1.5. So 1/2 of QP, which is 3, 1/2 of 3 is 1.5 centimeters. Alright, well now we have a right triangle and we have all the information that we can need to use our favorite little equation, the Pythagorean theorem. Again, just as a reminder, a squared plus b squared equals c squared. And they've done it a little bit different, so I'm just going to write it out how we normally talk about it. So we would say a squared plus 1.5 squared equals 3.92 squared. So a squared would equal, and a would then equal approximately 3.622. Alright, so that would be our apothem. So using that, we found our perimeter, we found our apothem. So, now we can use our area equation down here. So we'll say our 1/2 times our apothem, which we said was 3.622, times our perimeter, which is 24, which we found at the very front or the very beginning of the problem. So we would say this is 43.5 square centimeters. Perfect. Alright, so doing that much, I want to go over quickly the steps that I kind of have created that maybe will help us look through the problems a little bit easier. So my first step is, if you need to, and I would say most of the time you will, find your central angle. That is such an easy thing to do because you'll see later how important that is. Step 2 is to find half of the central angle to create your right triangle, which we had done over here in our black triangle. We took it out from our polygon. And then we're going to solve the right triangle. And remember, solving the right triangle means to find all the sides and all the length or angles, because that will help you distinguish your perimeter and your apothem. Next, just identify the side length that you need to put into your perimeter or to use, and then identify your apothem, and then solve. You know your perimeter is P equals the number of sides times your length, and then your area equals 1/2 your apothem times your perimeter. I'm going to move on through to show you the examples right now. The checkpoints, if you want to stop and try them quickly, you may. I'm going to stop this video and we'll do 11.6 continuation in our next video. But for now, let's make sure that we understand this information, and hopefully if you need to go back and restart it or go over some of the information again, that will be helpful. So I will see you soon. Thanks.